How are you? I have a Korean friend who decided that in raising his children in the United States, he would teach his child Korean. I think that happens a lot. When somebody comes over and their native tongue is not English and they decide to live in the United States, I don't have that distinction in that my family goes back in the U.S. before the Civil War. In fact, we still own land in West Virginia, which used to be Virginia, and we are claiming to be Appalachian Americans, and we teach our children how to speak like Appalachians. So when I say "how are you," that's Appalachian. H-I-R-E-Y-O-U. How are you? That's Appalachian. So as we go on, I will sprinkle the lectures with different Appalachian phrases. We were talking last time about the central limit theorem, and we actually proved the central limit theorem for a very specific case. Central limit theorem, again, is one of the most important of the theories, mathematical theories with engineering application, because statisticians and engineers use the central limit quite extensively. There's a question raised as to how fast does the central limit theorem, how fast does it converge? Specifically, if we have the average of a lot of independent random variables, how many random variables do we have to include in the average in order to make the approximation that the average is distributed as a Gaussian? Unfortunately, there is no quick response to that, except to say that it's pretty well application dependent. And I'm going to give you some examples, and these are straight from your book. If you recall, the central limit theorem had to do not with the probability density function converging, but with the cumulative distribution function converging. In other words, this normalized sum approached, I think it was the ERF of z minus 1/2, where the error function corresponds to the cumulative distribution function of the Gaussian random variable. So therefore, and actually this makes a lot of sense, especially if we talk about binomial random variables, because binomial random variables are pointy sort of things, and they have Dirac deltas in them. When you convolve them, you still have Dirac deltas, and how can you compare a bunch of Dirac deltas against a nice smooth curve? It's a little bit iffy there. However, you can very easily make a comparison between the integral of the continuous curve and the integral of the pointy things, the Dirac deltas, because the integral of the Dirac deltas is going to give you a bunch of steps. It's going to be a step sort of function. And you can see how close this step function is to the actual integral of the continuous Gaussian, or the error function. Here's some examples. Again, this is from your book. The first one's from page 281. This is the cumulative distribution function of 5 independent Bernoulli random variables with a probability of 1/2. So therefore, we do the following. We flip a penny 5 times, and we count the number of heads and use the average as the random variable, with a heads being, or a tails being a 0, the heads being a 1, and we come up with the cumulative distribution function, which is shown here. And you can see that for the repeated Bernoulli trials, again, for the density function, we're going to get a bunch of delta functions. For the cumulative distribution function, we'll integrate those delta functions and get little steps. And that's indeed what we get here, is we get a number of steps. These steps correspond to the cumulative distribution function of the average of a Bernoulli trial after only 5 iterations, and already we can see the discrete random variable beginning to mimic the continuous Gaussian random variable. If we look down at the second plot on page 281, this is the result of the repeated Bernoulli trials with a probability of equal to 1/2. And this is for 25 independent trials. Again, we obtain the stair step of the repeated Bernoulli trials, which of course is a binomial random variable. And if you remember, the binomial random variable converging to a Gaussian has a special name because historically it was found first, the Laplace-de theorem. So the Laplace-de theorem says that the staircase is eventually going to converge to the continuous error function. And indeed, we see here that for 25 trials that the convergence is relatively rapid. Let's take a look at another example. This is the sum of 5 independent uniform random variables over the set 0 to 9. So vision, if you will, rolling a die, except the die has 10 sides instead of 6. So the die has 10 sides. There's some of these old board games that had 10-sided die that you used to be able to roll. And these are equally probable. You would like to determine the distribution of the average of these rolls, and you're only going to do 5 rolls. This kind of corresponds to the convolution of the die. Remember, we did the die, and the rectangular 1 through 6 became a triangular 2 through 12. And if we did it again, it would be more of a bell-shaped sort of curve. This is very similar, except that the die now has 10 sides, and we're doing 5 IID random variables. So this is the 5-fold auto convolution of a uniform random variable with 5 equally sized spikes. And once we perform that convolution, we do the integral, and we get the very small staircase here. And as you can see, it approaches the error function very, very nicely. Let's look at some continuous cases. This is on page 282, by the way, at the bottom, figure 5-4. This is for independent exponential random variables with a mean of 1. In other words, the underlying random variable, for example, is e to the minus x times a unit step. So that means it has a mean equal to 1. This, if you recall, was the density function ascribed to some probability models and reliabilities, such as light bulbs and people. Suppose that we were to average, or I guess here we're not averaging, we're actually doing the sum. What happens if you average to the cumulative distribution function? If you have a sum and it has a density function which is spread out, and then you divide that sum by n to get the average, what does that do? That takes the scale and just pushes it into the origin by a factor of n, whatever that is. So it takes the underlying distribution and makes it more peaked by, again, kind of demagnifying the density function by a factor of n. So here we have the case of the cumulative distribution function. This is the sum of 5 independent exponential random variables with a mean 1. The cumulative distribution function of a Gaussian is right here. The 5 exponentials are right here. And that's kind of interesting, because maybe you wouldn't expect that if you took an exponential, an e to the minus x times a unit step, and convolved it with itself 5 times, you might think that, gosh, maybe we wouldn't have a Gaussian, but indeed we do. We get something which is very close to a Gaussian. This is the same exact exponential random variable, except for here there's 50 trials, and you can see that the Gaussian and the cumulative distribution for the sum of 50 of these independent random variables is nearly graphically indistinguishable. So here it takes 50 to converge. Anytime you say how long does it take for something to converge, you have to define what you mean by converge. Graphically indistinguishable is probably one way to do it. Now, here are convergences in terms of probability density functions. This is on page 286. Again, the challenge with comparing the Gaussian density function with the discrete random variable is that the discrete random variable is composed of little Dirac deltas. But suppose we took the probability mass of the Dirac delta and spread it out over an interval of 1 into kind of a histogram sort of flavor and represented the density function in that fashion. If we did this, we would obtain the type of result that we have on page 286. This is a binomial probability where n is equal to 5 and the probability success is equal to 1/2. So this is the average of, let's see. No, this is the summation of 5 random variables. And you can see that it pretty well is approaching a Gaussian random variable. But notice something interesting, as we talked about before. If we sum 5 binomial random variables, we cannot get a probability which is greater than 1/2, or greater than 5, can we? Because that's the maximum that can occur. We have successes on all 5 Bernoulli trials, and then the result is 5. Yet the Gaussian probability density function will continue on here out past 5 and will actually generate probabilities associated with that. This is due to the fact that the Gaussian is an approximation, and also for very large numbers in your summation, the numbers that you get by integrating this, by looking at the probability of mass of things greater than 5, are going to be so minuscule as to be comparable to 0. Lastly, we look at the case for the Gaussian approximation of the binomial probability with p is equal to 1/2, and n, which is equal to the number of trials here, is equal to 25. So we have something which is very, very close to the Gaussian. Again, we've taken the discrete probabilities and we've kind of spread them out. So you can see that the use of the Gaussian, or the central limit theorem, you will see that it's very, very useful, but it also is evident from the plots that we've looked at that indeed that these sort of things occur. What are the criterion for convergence of the central limit theorem? We have to look back to our initial definition of what the central limit theorem was. The central limit theorem was as follows. This is from your notes. We looked at the summation and then the so-called z factor, which took the summation minus n times its x value divided by its standard deviation. Notice that inherent in this definition is an assumption. And that assumption is that x bar, which is the mean of this random variable, that x bar does indeed exist. Let me try a pen here. This x bar here assumes that the mean of this random variable does not exist, or does exist, right? We're assuming it does exist. Similarly, when we have a sigma, we're assuming that the standard deviation of this random variable exists. So therefore, immediately we disqualify things such as the Cauchy. There's also the 1 over x for x greater than 1, which we said had an infinite mean. And all of those other ones are excluded in this particular proof. In fact, we know for the Cauchy, the central limit theorem does not work. But a sufficient condition is that there exists a finite x bar. In other words, x bar has to be defined, or it has to be not equal to plus or minus infinity, and a finite defined value of sigma, which is greater than 0. It has to be strictly greater than 0. If sigma is equal to 0, what sort of random variable do we have? We have a deterministic sort of random variable, don't we? So a criterion for this to occur is that x bar exists and that sigma b exists and be strictly greater than 0. Under those conditions, those are sufficient conditions for the central limit theorem to work. I also mentioned previously that the central limit theorem was applicable to cases more general than we have here. It's applicable to cases, for example, where the random variables are neither independent or identically distributed. In such a case, the central limit theorem will still work. The analysis is not as straightforward as it here, but it will still work. The assumption there, again, is that each one of the component random variables in the summation must have a finite variance and a sigma which is greater than 1. So therefore, if you have 1,000 Gaussian and 1 Cauchy random variable, that Cauchy random variable will spoil the whole application of the central limit theorem to the addition. Okay? Because that takes the average of the sum and makes it not defined. Okay, so any questions on the general application of the central limit theorem? Okay, good. Let's take a look then at confidence intervals. And we're going to look at, I think, kind of an interesting example on the application of the central limit theorem to an interesting problem. Confidence intervals. Recall Z is normal. That should be is, not n. Recall Z is normal with a zero mean and unit variance. In fact, this is many times called the Z value of a random variable obtained by subtracting the mean and dividing by the standard deviation. When we are talking about the specific case, let me get my pen here. Pen color, what color would you like? Red, very nice color, thank you. Okay, the Z value is always obtained by taking the random variable, subtracting the mean, and dividing by the standard deviation. When S is the sum of n IID random variables, then the Z value becomes the relationship here, where X bar is the mean of an individual component of that sum, and sigma is the corresponding standard deviation. We know then from the central limit theorem that Z is approximately normal under the assumptions that we state. Specifically, n has to be sufficiently large, x has to be defined, x bar has to be defined, and sigma must be a number which is greater than 0. The average, or the sample mean, is of course equal to the sum. A is equal to 1 over n times the sum. So we obtain the average by taking the sum and dividing it by n. Therefore, we have the following situation. If we take, instead of Z, we were to divide both the numerator and denominator up here by n. If we divided the S by n, we would get the average. If we divided the nx bar by n, we get x bar, right? And similarly, if we divide the denominator here by n, we get sigma over root n. So if we're looking for the Z value for the average, we take the average minus the expected value divided by the standard deviation. That then will also approach a zero mean, unit variance, Gaussian random variable via the central limit theorem, under the assumption that n is sufficiently large. This is something that we proved last time. So Z is normal with a zero mean and a unit variance. With that in mind, let's then look at the following probability. Let's assume that there's some value of Z, and we want to find that the probability that this average minus x bar over sigma over root n, which is our big Z value. Oh, that's hard to write. You know what that reminds me of? Kind of an Etch-a-Sketch. Do you guys know what an Etch-a-Sketch is? Okay. That is kind of like an Etch-a-Sketch. Okay. That's the big value of Z right here. And we know that if we were to look at this probability that minus Z is less than Z is greater than Z, that's twice the error function of Z under the assumption that Z is a normal random variable. And we will apply the central limit theorem to assure that Z is a random variable if n is big enough. And we have seen this. So just playing around with the, so is that okay? Twice the error function? Okay. Would anybody like me to show this? Are you okay with this? Okay, good. So with this in mind, let's just go ahead and manipulate this inequality. We're going to take sigma times root n to the other side, and then we're going to isolate the x bar. We're going to isolate the x bar in the middle. So we're going to do a little bit of inequality algebra to isolate x bar in the middle. Doing so gives us this result. Now, this is an interesting result because we have done nothing on the outside, so this is still equal to twice the error function of Z. But this is the probability that the average minus a number, that the actual average that we compute, this is the actual average that we compute, can be used to estimate the underlying mean. Now, the average is a random variable, right? This is what we actually compute when we do the experiments, take the summation and divide it by n. X bar, on the other hand, is a specified known quantity. The specified known quantity is the mean of the underlying density function, right? And what this does is this gives us the probability that the truth lies between a certain value and a certain value. Let me explain to you that in this situation. We have some sort of density. We don't know what this density is. This is f of x of x. And this random variable has a mean, which is x bar. And we don't know what the density function is. We don't know what the mean is. Yet what we do is we compute the average. We take IID samples from this, and we compute the average, which is 1 over n times the summation of some independent realizations here. The question before the house is, how certain are you that this average is equal to the x bar? Well, the chances of the average exactly being equal to x bar is 0, right? It can't exactly be that way. So what you would like to do is you would like to do the following. You would like to take x bar, and you don't know what the x bar is, but you can compute these two intervals. You can compute the average minus sigma z divided by, no, average minus, the average minus sigma z over root n, and the average plus sigma times the root n. And you can ask yourself, what is the probability that x bar lies on this interval from this point to this point? And the probability that x bar lies on this interval from this point to this point, imposing the central limit theorem, is twice the erf of z. Is twice the error function of z. Hence the concept of the confidence interval. Now, there's still some problems here. What's the value of z and what's the value of sigma, right? Those are two outstanding questions. The value of z is something that you determine, and it determines how tight or how loose your confidence interval is. For example, if you only want to be 50% sure, then you would choose, if you want to be 50% sure, you would choose one value of z. If you'd want to be 95% sure, you would choose another value of z. So it depends how confident you want to be that it exists within this interval. The other problem is not knowing what sigma is. And in general, we don't know what the standard deviation is. It's kind of curious, if you think about it, that we're attempting to measure x bar, and we're assuming that we know sigma. That kind of doesn't make sense. We don't know x bar. Chances are we don't know sigma also, correct? But there are certain problems where we can get around this. So let's go back to the overhead and address this. The problem is that we don't know sigma. Z is a parameter that we choose to dictate how confident we are concerning our confidence interval. So let's take a look at this. There are different solutions. One solution was given by William Gossett. He was the guy that worked for the Guinness Brewery and published a result under the assumption that the underlying density function up here, x, was Gaussian. So Gossett worked, what happens if we don't know sigma, but we know that the underlying density here is Gaussian? It's Gaussian, it has an unknown mean, it has an unknown standard deviation, but we know it's Gaussian. And we want to estimate the mean from this without knowing sigma. Gossett computed the so-called t-value, and instead of sigma, he used the so-called sample variance, which is an estimate of the variance which is made from the data, much like the average is. And with that, he found out that the underlying density function is a t-distribution with n minus 1 degrees of freedom. We mentioned previously why they called a student's t-distribution is because the brewery didn't want him to publish. So he published his paper under the name A student. and hence the name was a student T distribution because of that. Isn't that something? They wanted to concentrate on beer and stay away from mathematics. College is the opposite, right? Now, this is the PDF of a student's t-distribution with n-1 degrees of freedom. The student's t-distribution is pretty rough. It's one of those that you can't integrate, so the only way to evaluate probabilities from the student t is either through numerical integration. I'm not sure if MATLAB has a student t integral associated with it. It possibly does. There's no closed form integration available, and you must use a table. I have page 291 as there being a table. Yeah, okay. Here's the student's t-distribution on page 191 of your text. Can you read that? Okay. Here's the degree of freedom. This is n minus 1, and so that's the number of terms which are in the sum. You notice, interestingly, that the student t only goes up here to 60 degrees of freedom, and guess why? If you go beyond 60 degrees of freedom, the student t becomes indistinguishable from a Gaussian. Okay. And why does it become indistinguishable from a Gaussian? Because if n is big enough, this sample variance by the law of large numbers becomes exactly equal to sigma, right? If n is large enough, the estimate of the variance becomes exactly equal to the variance, and so we are left with essentially knowing the variance by the law of large numbers. So that's the student t's characterization of it. Again, the good news is that as n goes to infinity, the student's t-distribution with n-1 degrees of freedom approaches a zero mean unit variant Gaussian. And the reason it does that is because of the central limit theorem. Let's take a more, what I think is an interesting example. And this is the one that I promised you a while ago. This is the video guide 2001 by Mick Martin and Marsha Porter. And these come out every year, and in it they list all of the movies that are available that you can watch on television and videos. And every year they get thicker and thicker and thicker. I don't know if you've noticed that. So here's the question before us. I wanted to figure out how many movies that I saw, and I don't want to go through the whole book because there are 18,000 movies in there, and I didn't want to look at all 18,000 movies to determine whether I had watched them or not. So rather, I was going to randomly sample this book, certain number of movies, and determine whether or not I had seen the movies, and then if I computed enough of those, hopefully I could take the ratio of in my sample set, the movies I had seen, divided by the movies that I've looked at, multiply by 18,000, and get what's referred to as a point estimate of how many movies I've seen, right? The question, though, is how many movies do I have to look at to make sure that the estimate of the number of movies I've seen is close to the reality, to the underlying value? And how do I do this? If I looked at 4 movies and I saw one, then that would say I saw 25% of the movies, which is, what's 25% of 18,000? Yeah, 4,500. I saw 4,500 movies. That would be a so-called point estimate. But how sure am I that that's the true value? Point estimates do not tell you the certainty or the confidence interval associated with the estimation. So not only do I want that point estimate, but I want to be able to slap confidence intervals on this point estimate to be, say, 95% sure that I have seen between, say, 4,000 and 5,000 movies. I can be 95% sure if I sample enough movies looking through the Video Movie Guide 2001. Okay? So let's take a look at this. It turns out I chose 1,000 entries at random, and I saw 182 of the movies. That's a lot, man. Okay? And by the way, when you talk about random, you have to be very, very careful, because random means something. You got to make sure that you take out anything which biases your sample. You can't look at a movie and then look at the 3 movies following it. You have to actually choose a random page and then a random movie on that page. So that's the way I did it. I did it at a Starbucks one afternoon. Okay, so I saw 182 of them. Now the point estimates of the number of movies is as follows. I would take the average of the number of movies I saw, which is the ratio of 182 to 1,000. That's 0.182. And then if I multiply that point at 182 by the 18,000, my point estimate is that I've seen 3,276 movies in my lifetime. But again, the question is, how confident am I about that number? Is it a real sloppy number, or is it a very precise number? Perhaps during political campaigns you've heard about polls, and they say the poll is accurate to within 1 or 2 points. What they should say is the poll is accurate to a confidence of 95%, or whatever underlying probability they're using, to within 1 or 2 points. That means that the probability that they're choosing, say a candidate is at 0.48 or 48% of the vote, and they say plus or minus 2 points. That means it should go from 0.46 to 0.5, right? If it's 0.48, 0.6 to 0.5. There's also in that statement an underlying probability when they say it's within 2 points either way. They're saying that there's a certain degree of confidence that it's within those 2 points either way, possibly 95% or 90%. And a good poll will also tell you that probability. It's a confidence interval.
Is there a standard?
I don't know in terms of polling. The question is there a standard in polling where if they say plus or minus 2 points, what probability do they mean? I have no idea. I have never researched it. I do know that I have heard polls. I heard a Zogby poll one time where they actually mentioned the percentage associated with it. All the polls should indeed do that. If there's an underlying standard, I don't know what it is. Does anybody? No? Okay, I'm unsure. So here we have, again, that I've seen 3,276 movies. How certain am I that I have seen 3,276 movies? Well, here I can go back to my confidence interval. I'm going to do a 95% confidence interval. In other words, I want 2 numbers, and I want to be 95% sure that the true number of movies that I've seen is within these confidence intervals. Now, if I do that, then you remember that the confidence interval is twice the ERF. Now, why can I use an ERF in here? Because every time I hit one of these movies, I'm doing a Bernoulli trial, aren't I? I've seen it, success, or I haven't seen it, a failure. So each one of these that I have looked at is a Bernoulli trial. And what I have done, I have summed together, or I've averaged together, 1,000 of these. So my underlying density is that Bernoulli trial. I don't know the weights on the individual delta functions, but the underlying distribution on all of these has been 1,000-fold auto-convolution of those 2 little points underlying my original result. That's enough to apply the central limit theorem. We've seen that it works pretty well with much lower values than 1,000. And so with 1,000, we're going to have pretty accurate values. So with that, and the imposition of the central limit theorem, I can say that the underlying distribution is equal to a Gaussian. And if I put twice the ERF of z is equal to 0.95, I determine either through a MATLAB or a calculator function or through a table lookup that my value of z needs to be 0.98. Remember, the error function is something which you can only evaluate via a table lookup, or if you have it on your calculating machine, either as a, what did I do? Go away. Okay. The error function has to exist on your calculating machine, much like a sine and a cosine does. And just like there are inverse cosines and inverse sines, there are inverse ERFs. So I think you can see that z is equal to the inverse ERF of 0.95 divided by 2. So we compute the inverse ERF, and we get 0.98. So that's the value that I have. Now, you remember the other question. one question was the value of z. Well, that's determined by the confidence that I want. The other criterion is that I don't know what sigma is. I don't know what sigma is. For the student t, where I know the underlying distribution before we do the sums as a Gaussian, I can apply students t. In cases such as the binomial, which we have here, I can't assume that. But I do know something interesting about the binomial, which is the original result. And that is that the value of sigma squared for a Bernoulli trial is equal to p times 1 minus p. Remember that? And what I'm going to do here is I'm going to apply the value of p, the point estimate that I applied here, and I'm going to use that to estimate my value for sigma. And I can do this, again, because the underlying density function is a binomial random variable. Now, the question is, how accurate is that estimate of sigma? Well, here again, we appeal to the law of large numbers. And if we have, indeed, a very large law of large numbers, if we have a very large value of n for the law of large numbers, then this 0.182 is going to be pretty exact. It's going to be pretty good. Law of large numbers is working pretty well for a repeated binomial random variable. So we come over here. Okay, that's the error function table. I won't use that. I have this out of sequence. If you look here in the notes, you can see from an error function table where we get the value of z is equal to 0.98, because over here to the right is the error function table. You can take a look at that. Now, the result in the sigma z over root n then, n is equal to 1,000, sigma is equal to this number, and z, if we want 95%, is equal to 0.98 here. Which means that, if we come back to here, that the probability that the average minus p, minus sigma, I guess what is sigma? Root p, 1 minus p, z, over root n, is less than or equal to the average, the underlying x bar, which for the binomial is the probability of success, is less than or equal to the average plus this value. And let's see, here's what I want to do. I don't want to put the value of p in here, rather I want to put the value of the average, because it's the average we're using to estimate p. So I have all of these numbers available to me. And so from all of these numbers, I can compute this lower number, and I can compute this upper number, and give what is referred to as a 95% confidence interval for the parameter p, which is the average of a binomial random variable. If I do that, I find out that my value of p lies between 0.170 and 0.194. If I take this equation now and I multiply both sides by 18,000, which is the total number of movies within this book, and I'm assuming these are all of the movies ever made that I would have the chance of watching. If I multiply both sides of this by 18,000, I get that I am 95% sure that the number of movies that I have seen lie between 3,061 and 3,491. That's a much more definitive statement than saying the number of movies that I saw is, 3,276. But 3,276 lies right in the middle of this interval, doesn't it? Because I have a value plus an amount, the average plus an amount, and the average minus of the amount. So the average is right in the midpoint. So the average is the arithmetic mean point in my confidence interval. So that's kind of interesting. I've spent a lot of time watching movies, very clearly. Okay? Any questions on this? Okay. Hearing none, I think this would be a good time for a break. Let's go ahead and take a break and meet back here when the big hand's on the 5. Here we go, 5, 4. 2 points before we start into the lecture. First of all, I was caught in a misstatement. I actually didn't count that I did. How many movies? I didn't do. I made those numbers up. Somebody computed it between class. Was it? And how many movies would I have to see to do that?
About two or three a week.
2 or 3 a week for how many years?
For your whole, I assume you were 45. I don't know how old you are.
There you go. Okay. So I'd have to see 3 movies a week my entire life if I was 45. Okay. And see, that's okay. That's very interesting. So it was kind of made up. Although, interestingly, that figure is probably not far from accurate. I enjoy a good movie. I don't have cable, so I watch movies. Big difference. I enjoy a good movie. I enjoy a bad movie. I like all movies. The other point is that you should know that in terms of announcing tests 2 weeks in advance, that I am totally vindicated. That there has been I've had some of my crack people look at the first tape, and it was clearly said 1 week notice for the test. So you should know that. The verdict recently came in, so that was good. Okay, we want to talk now about a new chapter and a new concept and a new idea. The name of this course is Introduction to Random Variables and Random Processes, I believe, something like that. Anyway, random processes or stochastic processes are in there. Random processes is a synonym to stochastic processes, and we will use the terms interchangeably. You use the word stochastic when you like to impress people because they might not know what it is, whereas everybody knows what random is. So a stochastic process and a random process are exactly the same thing. There are some fancy, precise mathematical definitions of a stochastic process. I'm going to define it in an engineering sense. I like engineering senses. I still remember as an undergraduate, I had an engineering prof define to me what a continuous function was. The mathematicians will tell you that a continuous function, there's all these limits. If it's continuous at a point, that the limit going this way must be equal to this way and things like that. He said, no, a continuous function is any function you can draw without lifting your pencil off the paper. That's a continuous function. So I always like that definition. So let me give you a similar definition for a stochastic process. A stochastic process is nothing more than a random variable that is a function of time. It's a random variable which is a function of time. Now with that, there's some different caveats. It can be discrete time, as in the case of a discrete signal. It can be continuous time for continuous signal. And it really doesn't even have to be time. It can be spatial coordinates also. And there's some interesting differences between spatial coordinates and temporal coordinates. We all know, for example, that there is noise on a television screen, or noise which you might get quantization noise from a very lossy JPEG compression. And so in that case, we have a random variable which is not a function of time, but is a function of space. As engineers will introduce the concept primarily as a random variable, which is a function of time. We many times think of stochastic processes as models of noise. That's true. In fact, they're very, very valuable models of noise, but they are also very valuable models of information-bearing signals. For example, my lecture to you today is stochastic, because if it were deterministic, you would know what I was going to say, and you wouldn't have to be here, right? So because of that uncertainty of what's coming in the future, my lectures are stochastic in a way. Not random, but stochastic. Also, in terms of computer communications, when you have packets arriving, for example, at a computer, many times those are modeled as a stochastic process referred to as a Poisson process. Very popular model in the study of computer communications, and we will be looking at that also. So again, definition of a random process is a random variable which is a function of time. Let's see if we can get our hands on this in some sort of fashion. When I say that there's a random variable, and I say, okay, it's a Gaussian random variable, I do the experiment, and the outcome is 5. Can I ever say that? No, because after I've done the experiment, it's not a random variable anymore, it's something I know, right? A random variable is something that you say probabilistically about an event which happens in the future. Therefore, in a similar sort of fashion, when I do a stochastic process, and I write down a function of a stochastic process, say that something that goes like this, this is not a stochastic process anymore because I've written it down. It's a realization of a stochastic process, right? Nevertheless, uses of plots like this will be necessary in the explanation of stochastic processes. There's many types of stochastic processes with which you can generate. Probably the most familiar is with white noise. White noise that you hear from different sources. White noise has a hissing sound, kind of a shh, and we will discover in the class exactly why they call it a white noise. There's also color noise, corresponding to one of the most beautiful, peaceful sounds, sleeping under a metal roof and listening to the rain hitting the roof. When you pop popcorn, there's a pop, 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 pop. That's also a stochastic process because it's something which you can't specify deterministically. Many of these have characteristics associated with them, and many of them we will assume we can repeat. Much like we can repeat a Bernoulli trial a number of times, we can repeat a stochastic process, a realization of a stochastic process a number of times. For a pedagogical example, suppose that we had a scope and we found out that when we turned off the lights, there was an arcing which set out a little electromagnetic field, which just gave us kind of a noise scope on the oscilloscope trace. So suppose that the noise trace on the oscilloscope went something like this. So that was the first time, and then it went to 0. So it was a transient sort of phenomenon. We did the experiment again, and this time it did something a little bit different, but it kind of looked the same. And this would be our second realization. You notice what we're doing here is we're accumulating stochastic processes, much like we would accumulate IID random variables from a repeated experiment. We're doing a repeated experiment, but instead of just gathering a single number or a vector of numbers, we are generating an entire function from each of these processes. And we could do this for n times. So let's suppose we go down here and we do x sub n of t, and we get something which looks like this. Now there's some assumptions that I'm making, one of which is that the source of the noise, that's contracted to source, the source of the noise is time invariant, in the sense that the statistics don't change from one point to another. I could, for example, have I'll say a fluorescent light which also interrupted my scope traces, and maybe if in the second half the fluorescent light was on and the first half it wasn't on, then this wouldn't be time variant because the conditions under which the experiment were performed changed. So time variant means the system itself is invariant. So I get all of these things, and there's some questions in my mind which I can answer here. One of the questions is there a expected value or an average of this stochastic process? And the answer is yes, there is an average of this stochastic process, or a mean, I should say a mean of this stochastic process. And just like in random variables, how does one estimate the mean? One estimates the mean with the average, correct? And we can literally estimate the mean, or the expected value, of this stochastic process with the average. In fact, it's referred to as an ensemble average. And the ensemble average would be obtained by a function which we would call the average as a function of time, which is equal to 1 over n times the summation of the individual stochastic processes. Let's say n, better make this a capital N. So it's an average, and we would find out that indeed, as we averaged more and more of these, that there would be an average value to which this process would converge. And this average, just like in random variables, would be an estimate of the mean or the expected value of x of t. And we will be talking about the expected value of x of t. Another thing we can talk about is the probability density function of a random variable. Of a random process. Here we have a stochastic process. What I'm going to do is I'm going to choose a point on this time axis. If I choose a point, say t is equal to tau, there's going to be a number associated with the function here, which we can call x of tau. Remember, a stochastic process is a random variable which is a function of time. So x of tau is nothing more than a single one-dimensional random variable. It is a random variable. And every point on here is a different random variable. Let's just look at the random variable associated with tau. If this indeed is a random variable, then there is a density function associated with this random variable. In fact, this random variable can be represented as f of x of tau of x. This means this is the density function for the random variable at the point tau. Now, here's a question. Is there a way that we could generate this density function from, say, an ensemble of realizations, say, of the light source going on? How do we do it with a single random variable? One of the ways that we kind of explained it was in terms of a histogram. Remember, a histogram, when appropriately normalized, if the number gets big enough and the bin sizes become small enough, will approach the underlying probability density function of the random variable. Do you recall that? We can use a similar sort of process to estimate the density function for this single point. By the way, once we get the density function for this point, in general, it tells nothing about the density function for this point, or this point, or this point, or this point. They could all be different. But we're just zeroing in on a specific value of the realization, which we know is a single random variable. We could generate this from an ensemble average by going x1 of t, x2 of t, all the way down to x sub n of t. And let's use our light switching on thing again. We get some sort of transient here. And what we're going to do is we're going to choose a value of tau here. And we're going to go down, and for this value of tau, notice that we glean off of each one of these realizations a random variable, don't we? Off of each one of the random variables, we glean a value. So this is x sub 1 of tau. This is x sub 2 of tau. This is x sub n of tau. These are specific numbers, and then we can take these specific numbers and we can do what? Lump them together in a histogram, right? So we can lump these together in a histogram, if you will, and this value, let's see, let's do it this way. No, gotta do it this way. Want the value to go up. I'm having perspective problems here, ladies and gentlemen. Let me I guess I can do it that way. Okay, for example, this lies within this bin, so we put a value here. This lies in a bin a little bit above it, so we'd have a value of 1 here. This lies a little bit below it, so maybe we'd have a bin here for this one, and we would keep building up the histogram in this fashion. You get the idea? And eventually, if we had our bin sizes sufficiently small and our number in our ensemble sufficiently large, we would generate a nice smooth curve which would approximate the density function for this stochastic process at this one point in time. Does that make sense? In a similar fashion, we could go over here to some other value, say, say a value of C. And we could generate all of the points over here, one value at a time. And if we did that, we would get some other sort of density, which need not be the same density as we did for the value of tau. And we can do this for every point on the line. Now, we know the following, that each one of these density functions has a mean associated with it, right? And for each one of the density functions, we could go across and we could actually plot the mean of the density function as we went across. If we did that, what function would we get? If we just plotted the mean of the density function, the expected value of the density function with respect to time. If we did that, we would obtain the expected value curve that we have over here, because this is nothing more than the mean. So you can see this density function not only contains the concept of the average in it, estimating the mean, but it also has some other things. What does it mean if the variance of this density function is large? It means that if the density function of this is large, this means that these points go over a very large range, don't they? The points go over a very, very large range if the variances are high. This then gives us to the second moment, or the standard deviation of the stochastic process, which tells us how much the stochastic process varies around a point. Let me give you two examples. Here's one example. This is our x sub 1 of t, x sub 2 of t, and x sub 3 of t. And then the second example that we'll have, and this will correspond, by the way, to a small variance. Over here, we'll talk about something which looks like this. And you can see it looks kind of like this is this with a bunch of squiggles on top of it, right? Let's call this y. y1 of t, y2 of t, y sub n of t. Now, we come down here and we can compute the average of these curves. And suppose the average is this way. That's the average of these curves. Also, assuming that the average is close to the mean, we can do the histograms, and the histograms will be centered around the average. For example, if we did the histogram at this point, the histogram would look like this because it would be centered around that value. The histogram here would be centered around this value, etc. Does that make sense? So there are histograms around each one of the individual points. The variance of the histogram tells us, if you will, the certainty of the average. If we were to do the same exact result over here, and we were to do the average, we might get exactly the same average. In fact, it looks like the wiggles just might average out. The upward wiggle would cancel the downward wiggle. However, if we were to do a histogram at some point here, we would find out that that histogram would be much more spread out. It would be much more spread out because the values along this point at tau can take on bigger, a much larger range of values. So the histogram could be much, much bigger here. And in a similar fashion, we could have a histogram over here, and we would kind of expect that the histogram here would be much, much larger and much more spread out than it would be here. What we can do in each case is we can look at the mean plus, say, one standard deviation of the histogram. So we go one standard deviation, and if we did that over here, we would get something which looked like this. Because, again, the density functions are relatively close together. Over here, we would get a value which would be much larger, a much larger band of uncertainty, because the density functions are much more spread out. This distance here is the square root of the variance of x of t, if you will. Because it tells us how much the underlying stochastic process wiggles. And over here, this would be the variance, of y of t, the square root of it. Many times you will hear stock reports talk about the volatility of a stock. The volatility is nothing more than a measure of the variance. If you have a stock whose prices go like this, it's not a very volatile stock because its underlying stochastic process is smooth in some sense. If you have a volatile stock, then that stock will go just crazy. It'll go crazy like that. So the blue is referred to as the price movement of a volatile stock, and it corresponds exactly to having a big standard deviation. In fact, this is exactly the parameter that people in finance use to measure volatility. It is the variance. It's the uncertainty of the stock around the mean. So the blue would have a lot of volatility, whereas the red would have little volatility. Volatility is a synonym for the standard deviation of the underlying stochastic process. Yes?
But you've only got one sample with the...
Oh yeah, that is a big problem, isn't it? And that's the reason that the comment was we only have one sample here associated with the result. Yeah, and what is typically done is that, let's see, what is done? By the way, instantaneous estimation of the volatility is one of the big questions, which is before traders. I had a floor trader tell me one time that if one could come up with an instantaneous measure, an instantaneous estimate of the true volatility, that he could be rich. That's what he told me. I don't know.
But I mean,
These are wacko. Okay, your question is, there isn't sufficient information here to do an ensemble average, right?
not exactly.
Oh, this.
I mean, you said that's the variance, but the variance of one number is 0. I mean, if you only have one sample, then the variance, there's no variance.
Okay,
You
2
know what
points.
the underlying mean is.
2 points. 2 points. There is a concept which we'll get to later on the course referred to as ergodicity. With an ergodic stochastic process, you don't need an ensemble to estimate averages, that the averages and the means and such are already buried in a single realization of the stock. Number 2 is the way that this is typically done in the market is to compute the average here over a window. They do a lot of windowing in terms of things, to compute averages over windows and assume things are, say, linear, for example, within windows, and then compute corresponding volatilities. But the fact that these are not realizable as a set of ensemble averages reveals finance as soft science. It is a science whose theories cannot be verified, because the underlying stochastic processes which are generated in finance are not repeatable. They're not verifiable as they are in engineering. Finance is indeed a soft science, one that, again, can't be verified. So you can tell your success by, well, in finance and traders, what kind of car you drive. That's basically the measure of success. Unfortunately, that's not always the ability to trade well. Many times it's your ability to attract funds, which is a different dimension. So anyway, can we obtain from an ensemble this variance? Well, yes, clearly we can. We can get that variance one way by computing the histogram, then using that as a PDF, and then computing the standard deviation of the PDF. We can certainly do it that way. But another way to do it with the ensemble average is to do the following. Suppose we come back over here and we have this same sort of ensemble, and we would like to compute not only the average but the variance, the standard deviation, at all of these points. One way to do that would be to, again, compute the average. And then to compute what is referred to as the second moment. We would take each of these functions and square them, and I mean square them point by point. Whatever that number is, you compute it by its square. So if we were to square this process, we would probably get something like this. The square of 0 is 0. Clearly, this would be rectified and increased. So x1 squared might look something like this. So we would take that value and square it at every point. Then we would add up the squares and we would average the squares, and this is something we can call the second moment. The second moment of the stochastic process. Then the variance of the stochastic process, see if this looks familiar, is equal to the second moment minus the square of the first moment, to a good approximation. And again, we would apply the law of large numbers to say that as n increases, that this variance estimate will become more and more accurate. Okay? So this is exactly the same thing as the variance. This indeed is the variance applied 1 point at a time. That is, when we look at the variance at some value of tau, we're only looking at the second moment of that value of tau and the average at that value of tau. So when we compute the second moment and the average here, we only use these points. We only use the points associated with tau. We don't use any other points in the whole probability density function in order to find the second moment. By the way, somebody said to look at the stochastic resonance movie. Somebody sent me an email. Was that in here? Anybody look at that stochastic resonance example over the streaming video? Okay. No one did. Have to look at it. Somebody said it looked really weird. Maybe due to aliasing effects at all. Well, all of this that we've done so far is referred to as first-order statistics. Why is that? Because we have isolated a single point in the density function, and we have looked at the statistics along that point for the ensemble. Okay? What about second-order statistics? Indeed, if we take a stochastic process, x of t, and we can choose 2 points, say a value of t and a value of tau. And here we get 2 random variables, x of t and x of tau. Maybe I should use a different variable here. Let's use c, so we don't get confused with the value of t here. Okay, a stochastic process is a random variable which is a function of time. Here we have chosen 2 values, and we're going to assume that c and tau are numbers which have been specified. We know what they are. So we have a random variable at c and a random variable at tau. We have 2 random variables. These random variables can be interrelated to each other. Especially, I think you can see that in many cases, if tau is close to c and we have kind of a smooth curve, certainly they'll be related to each other, right? So, therefore, we have to characterize these 2 random variables by a 2-dimensional probability density function. So in the case of second-order statistics, we take a look at 2 points at a time. We need to characterize the second-order statistics by a 2-dimensional probability density function. So we can talk about f of x at c and x at tau. These are our 2 random variables as a function of x1 and x2. And many times in the notation for the stochastic process, the time variables are put here to remind us that let's see, c and tau, that the probability density function is a function of our choice of c and tau. Clearly, if we choose different values of c and tau, we're going to have a different density function. So many times that explicit relationship is emphasized by putting a semicolon and the realization that this density function is going to change as c and tau vary. So this is the second order characteristic function of the stochastic process. Is there a way that we could characterize this second order density function from an ensemble average? And the answer is yes, and let me illustrate how we would do that. Suppose we had, as before, our ensemble of different realizations. And we will assume specified values of c and tau. So for a given value of c, we have capital N statistics for c, and for tau, we have capital N statistics for tau. And what we would like to do is, from these ensemble values, empirically build ourselves a probability density function. We do this much like, remember the weight and length probability density function description for the trucks that came in? We do exactly the same thing here. We build a two-dimensional histogram, and this two-dimensional histogram, as the number of n goes to infinity and the bin size shrinks to 0, when we normalize it to a unit volume, will take on the shape of the underlying two-dimensional probability density function. We do this as follows. We take the x1, and this corresponds to the random variable c, and we're going to take the x2, and this is going to correspond to the random variable tau, and we will, in the spirit of a histogram, block it off into quantized bins. We go to the first case, and we see that x1 of tau, let's see, now x1 of c, say, lies in this bin, and x1 of tau, say, lies in this bin, so therefore we add a value here. So each one of these gives us a single point on the two-dimensional histogram. So we're building these up like Legos, right? Stacking up Legos. So we go to the next case. Okay, it looks a little bit higher, a little bit lower here. Here, I don't know, I would say it would be here. So we would continue this process for all of the different values of n. And we would tally the values in each one of the bins. We can view this then as a histogram with little blocks sticking up, in this case 3 units, in this case 2, in this case 5. If we did this, the number of n went to infinity, the bin size shrunk to 0, we would asymptotically approach the underlying two-dimensional density function for this value of c and tau. So does that make sense, that we have the ability to empirically generate these two-dimensional probability density functions from an ensemble average? In fact, all of the statistics that we see that we can do this sort of thing from, which is very interesting. Now notice something also that's very interesting is that the density function changes as a function of c and tau. If I were to choose a different value of c and or a different value of tau, my underlying probability density function changes in general, right? So you can see that the description in one dimension is really rough because I have a point, I have a different density function for each different value of t in one dimension. In 2 dimensions, I have a different two-dimensional probability density function for every value of tau and c. If I have an underlying probability density function, I choose a value of tau and c, then for this single point, I have a two-dimensional density function corresponding to it, right? And if I have a point here, I have another two-dimensional density function ascribed to it. You see, it gets pretty complicated pretty quickly, right? Well, what do you think's next? 2. I mean, if we have a continuous function, we go 3, in which case we have a 3-dimensional underlying density function that's going to be a function of the location of the 3 points that we choose. We can do 4, we can do 5, we can do 1,000,000 and have a 1,000,000 point probability density function, right? If we had a density function and we chose 1,000,000 points on here, we could actually do a 1,000,000-dimensional probability density function. And this becomes unwieldy. What's interesting is that in order to uniquely characterize a stochastic process, we need to know all of these density functions. That's too much to know. Do you agree? It's too much to know. So, engineers, clever people that we are, have found out that in many cases of interest, that second-order statistics suffice for our purposes. For many cases, second-order statistics suffice for our purposes. In fact, we will be dealing very extensively with second-order stochastic processes. Furthermore, there is an interesting property of the Gaussian probability density function. And for a Gaussian stochastic process, what do we mean by a Gaussian stochastic process? We'll define it more rigorously later. But it means that any 2 points you choose, that the 2-dimensional underlying density function is a 2-dimensional joint Gaussian probability density function. It turns out that if you know all the second-order statistics for a Gaussian, if you know the second order, you know the third order, fourth order, fifth order, billionth order. The second-order statistics define all the higher orders. It doesn't work for any other density function, but it does for a Gaussian stochastic process. So that's an interesting result. Let's then define some of the parameters associated with a density function. We have kind of made some teasing pokes around the boundary, but let's look at a definition. One of them is the expected value of a stochastic process. The expected value of a stochastic process is the expected value of the stochastic process at every point in time. It's a first-order statistic and only is concerned about the realization of the stochastic process at a value of t. As you might expect, this is equal to the integral of x times f(x) of t as a function of x, and then again we explicitly put that this result is going to be a function of t times dx. So this is the density function at the point t, and we compute the value thus that way. Let me give you an example. Suppose that x of t was a random cosinusoid. With a random amplitude. We're going to assume that the frequency is fixed, and we're going to assume that the amplitude is a random variable, and that this random variable is uniform on the interval of 0 to 1. So the density function for A is uniform on an interval, say, from minus 2 to 2. So it has a value of a height of a fourth. So you get the idea? We're going to choose a random variable from this density function, then go to an oscillator and generate this function. That's going to be our stochastic process. And you can see it's a random variable that changes amplitude. I'm sorry, x of t changes with respect to time. What is the expected value of x of t? Can you tell me just by looking at this what you might expect it to be? Here's one realization. Here's another realization. Don't forget, A can go negative, right? Here's another realization. All of these are supposed to have the same value of omega. Here's another realization. If you averaged all these up, anybody give an idea what the expectation would be? Yeah, 0. Because of the symmetry here. We'll actually show this. Notice also that this is not a stochastic process for all values of t. If we were to choose, for example, the point omega t is equal to, what is it, pi over 2, 90 degrees, this cosine goes to 0, and all of these functions will go to 0, right? So x of t, x evaluated at t is equal to pi over 2 omega, is equal to 0, which is deterministic. So it's not stochastic at all points. There are few points corresponding to 0 crossings where it's deterministic. So clearly the density function changes at every point in time. We have a density function and a random variability here at the origin, but right here at pi over 2 we don't. So the density function as we move along t is indeed going to change. Do you agree with that? So what is the expected value of x of t? The expected value of x of t, here we get back to that basic definition. We can determine the expected value of x of t by integrating whatever we're expectating over a density function describing the random variable component. So this is equal to the integral of x of t times the density function of a, because that's the only random variable in here. And we know that x of t is equal to what? A times the cosine of omega t times the density function for a, dA. Now, in computing these integrals, you'll find out that you're integrating with things that you're not used to integrating with respect to. We're used to integrating, for example, with respect to t here. We're not integrating with respect to t. We're integrating out the stochastic random variable. And this turns out to be a random variable with a value of 1/4 over the interval from -2 to 2. And we can actually factor out the cosine omega t, right? Because that's not a function of what we're integrating over. And we have f sub a of t, which in this interval is 1/4. Integral from -2 to 2 is dA, which is what? Clearly 0. So the expected value of the stochastic process is 0. You agree with that? I see some crinkled brows. Integral from -2 to 2 of 1 is 0. What? What did I do? Oh, I forgot my A. What's wrong with this picture? It's still 0. Okay. It's still 0, right? Still 0. Sorry about that. Before it wasn't 0, it was 4, right? But now it's 0. Yes. So indeed it is 0. And the way you can justify this in your head is if you do an ensemble average, every time you have a positive wiggle, you're going to have a negative wiggle with the kind of an equal probability that's going to cancel it out when we add the two together, right? And this curve plus this curve gives a 0. So everything above the line, you have something equally probable below the line, so it will average out to 0. Now, and the last thing we want to look at, let's look at the variance of this stochastic process. Before we do it, let's see if we can intuitively figure out what it is. At the 0 crossings, what do you think the variance of this stochastic process is? 0. It has to be 0. At the top, notice that at the origin, for example, here, that the random variable is simply equal to a, right, at the top? So we would expect the variance at the origin here to be the same as the variance of a, since at the origin it's equal to a. So no matter what this variance is, it has to be equal to the variance of a at the origin and equal to 0 at the 0 crossings. Let's see what our math tells us. The second moment of x of t is equal to the integral of x squared of t times the density function of a, dA, which is equal to the integral of a squared times cosine omega t times f sub a of a. we can factor out the cosine and recognize that a goes from -2 to 2 with a value of 1/4 of a squared dA. And so this becomes what? I'm sorry, I forgot the square on the omega, didn't I? $16? Is that right? So that's 4/3 cosine squared omega t, which is also equal to the variance of x of t. Why is that? Because the mean is 0. The mean is 0, the second moment's equal to the variance. The mean is 0, so the second moment is equal to the variance. Okay, well, let's look and see what this looks like. If we look at this, here's our initial stochastic process. It kind of goes down like this, right? And here are the zero crossings of the original stochastic process. This has a variance of cosine squared, and it has a value of 4/3 at the origin, and it's a cosine squared which goes like this. You'll notice the variance always has to be non-negative. So indeed it is. The variance is non-negative. So we see indeed that we have a zero variance at the zero crossings of the stochastic process, and we have a maximal value at the midpoints between the zero crossings, as we might have suspected. And indeed, the value at the origin, the 4/3, that is equal to the variance of A. That is equal to the variance of A. So this is an example of computing the mean and standard deviation of a simple stochastic process. Any questions? Okay. Thank you, then. That's it.